In this section, we're going to talk about power series. So we'll begin just, take a look at this infinite series right here. Right, so that's a generic infinite series whose terms are the nth term is a sub n times x to the n. So we have these powers of x in there. It is essentially an infinite degree polynomial. We call that a power series. Now, this is a power series that's centered at 0, at c equals 0. But we could center it anywhere, and in general, if I have a power series whose terms involve a power of x minus c instead of just x, we say that that is a power series centered at c. So some examples. Here's a couple of examples here. We've got a power series centered at 0. The nth term is x to the n over n factorial, and we've written out the first few terms there. Here's a power series centered at 1. That's 1 over n times x minus 1 to the n. That's the nth term, and we've written out the first few terms there. So the power series, a power series we could think of as a function because there's a variable in it, right? Like if we plug in a value for x, it will result in a specific infinite series, which may or may not converge. And we could think of it as a function whose domain is just the set of x values that make the series converge. So we'll note first that every power series will converge at its center. And so that center, C, is always in the domain. And what we're going to focus on in this section is if we're given a power series, can we determine where else it might converge? And there's 3 possibilities. It's possible that you get convergence only at the center, and if you stray from the center even just a little bit, it'll make the series will blow up. It could be that you can stray a certain distance from the center, but only so far. So if you stay within that distance, you get convergence, and if you move outside that distance, it'll diverge. And that distance we call a radius of convergence. And it's also possible that your power series will converge for all values of x. Basically that you have an infinite radius of convergence. And the set of values, so the radius of convergence sort of tells you how far you can stray, right? So if it converges only at the center, then the radius is 0. If it's possible that that radius is some finite positive number, so you have some distance that you can stray. If your power series converges everywhere, and that domain is all real numbers, then in this case the radius of convergence is infinity. So the radius is how far you can stray from the center and get convergence, and then if you take that and then look at the interval of values that defines, we call that the interval of convergence. So our focus is on finding the radius and interval of convergence. We're going to start first by just how do we get that radius? And to do this, we use the ratio test. All right, so here's a power series that they gave us, and if we're using the ratio test, we know that we're going to take the ratio of the n plus 1 term over the n term and see what that limit is. So because these terms now involve variables, they're not just constants, usually we switch from an to un. That's sort of just a convention. But here's the nth term. Here's the n plus first term. So we'll just note first, this involves powers of x. So we know that it converges at its center, and that center is 0. So we know it converges at x equals 0. Now, if x is equal to 0, the series we get looks like this. The first term is 1, and then every other term is 0, because we have powers of 0. And so this is just 1. And just as a quick reminder here, at n equals 0, 0 factorial is equal to 1 by definition. All right, so now what we're going to do is consider any fixed value of x that's not 0. So this part here is important. I'm going to set up this limit, and then I'm going to talk about why we want to make sure we're considering some fixed value of x. We're not actually fixing a particular value of x, like I'm not saying let x be equal to 3 or something, but as we set up and move through this limit, x is just some fixed but arbitrary constant. So let's set up our ratio test. This is the limit as n approaches infinity. U sub n plus 1 over u sub n. And this is the limit as n approaches infinity. U sub n plus 1, that's n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. Now we're going to do some simplifying. N plus 1 factorial is n plus 1 times n factorial. And let's see, I guess one thing we could do is simplify the powers of x here. So x to the n cancels, and we're just left with x to the first up top over n factorial. And now those n factorials cancel. So we have the limit as n approaches infinity of n plus 1 times x. Now here's where it's important to understand that x is some fixed, but arbitrary constant, and that this is a limit as n approaches infinity. X isn't doing anything, right? It's just sitting there. And for that reason, we're actually allowed to grab this value of x and bring it out like because it's some fixed constant, and bring it out front. We're taking the limit as n approaches infinity. That x is fixed. When we take it out, though, we have to remember x could be positive or negative. So what we have to do is take out the absolute value of x, right? This is all sitting inside a set of absolute value signs. So we have to take out absolute value of x and then times the limit. Now, we don't need absolute values here. I mean, we could have them if we want, but we don't need them because it's a limit as n approaches infinity. So clearly, those are going to be positive values. And now for any fixed value of x, whatever x, for every non-zero fixed value of x, this limit is infinite here. And then I'm multiplying it by some non-zero constant, then that whole thing is still going to be infinite. Now think about what we do with the ratio test. With the ratio test, we evaluate this limit, and then we make our decision based on whether or not this is bigger than 1 or less than 1. And infinity, certainly bigger than 1. It's bigger than 1 for all x. No matter what the value of x is, that limit is going to be bigger than 1. So that means that for any value of x, The limit is always bigger than 1. And that means that this series diverges for any non-zero value of x. That means that we can't stray from the center at all and get convergence. So the radius of convergence is equal to 0. All right, so let's try another one. We're going to find the radius of convergence for this series. The nth term is given by 3 times x minus 2 to the 0. So when I'm working with these series, the first thing I like to do is just make a quick note. I'm looking at the powers of, in this case, x minus 2. I know that this is centered at c equals 2. And so for x not equal to 2, if we consider some arbitrarily fixed value of x that isn't the center, that is not 2, we're going to write out these, the nth term and the n plus first term. So, and set up our limit. The limit as n approaches infinity of u sub n plus 1 over u sub n. This is the limit as n approaches infinity of 3 times x minus 2 to the n plus 1 over 3 times x minus 2 to the nth power. We do some canceling. So the x minus 2 to the nth power, all of those are gone. We're just left with x minus 2 to the first power up top. And of course the 3's cancel. So we have the limit as n approaches infinity of the absolute value of x minus 2. Again, so look, we're taking the limit as n approaches infinity. There's no n's left, right? So whatever absolute value of x minus 2 is, that's what this limit is. Right? That's what we get. There's no n's here to even allow to let get huge. So like we're kind of done with this limit. Now, what we got is an expression, right? And what we have to remember is we're finding, we're conducting the ratio test. And with the ratio test, we get convergence whenever the limit is less than 1. We get divergence whenever it's greater than 1. So we know that this series converges when absolute value of x minus 2 is less than 1, right? And diverges when it's greater than 1. So let's focus on what gives us convergence. Absolute value x minus 2 less than 1. Well, that means that if the absolute value of x minus 2 is less than 1, that means that x minus 2, that the absolute, sorry, not the absolute value, that means that x minus 2, without absolute values, has to be between -1 and 1, right? That's what makes its absolute value less than 1. And if we add 2 to all 3 sides of this inequality, we get 1 less than x less than 3. So we were close to finding out, I guess, what the interval of convergence is. We certainly have a range of values. We'll just note that we don't know what happens at the endpoints yet. So we know that it converges on the open interval from 1 to 3. We'll talk about endpoints a little bit later. The radius since it's centered at 2, this inequality tells us that the radius is equal to 1. Of course, the radius looks like that's what they were asking us for. So just a quick note that we know that we get convergence on the open interval (1 to 3). So the open interval meaning not including the endpoints. We don't know what happens at the endpoints yet. And we'll talk about that a little bit more later. All right. So let's take a look at another one. We're going to find the radius of convergence for this series. I guess we'll start by just recognizing, we have powers of x here, right? X to the 2n plus 1. So that means that this is centered at 0. So now we're just going to consider non-zero value of x. We have our nth term. Our nth term is -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, and then u sub n plus 1, -1 to the n plus 1. Let's see, x to the, got to be careful here, 2n plus 1 plus 1 over 2n plus 1 plus 1 factorial. So 2 times n plus 1 is 2n plus 3. And now we can set up our limit. Okay, so the n plus 1 term goes first. Now these are both fractions this time, so I'm going to start with the n plus 1 term and then just multiply it by the reciprocal of the nth term. So times 2n plus 1 factorial over -1 to the n times x to the 2n plus 1. Now the powers of x, those are pretty easy to cancel out. The 2n plus 1 factors of x in the bottom, those are all gone. And we have 2 more factors of x up top because that power is 2n plus 3. So we end up with x squared in the numerator. And let's see what's going on with these factorials. So the 2n plus 3, right, that's bigger than 2n plus 1. So just maybe a little bit of side work here. 2n plus 3 factorial. That's 2n plus 3 times 2n plus 2 times 2n plus 1 all the way down. So times 2n plus 1 factorial. So we can see that the 2n plus 3 factorial contains all the factors that 2n plus 1 factorial has. So I'm going to rewrite this in that way so that we can get it to cancel. Also, just notice all of this is happening inside absolute values. So I'm going to just not worry about those powers of -1. Whether it ends up being negative or positive for any given term, In fact, actually, it would be negative, right, because we have one more factor of -1 than we have on top than we have on the bottom. So that'll end up being a negative. But it's inside absolute values, so I'm just going to ignore that. And I'm going to rewrite this. So I've got x squared 2n plus 1 factorial on top. On the bottom, 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Now we could cancel these factorials here. And again, so we're finding a limit as n approaches infinity. X is staying put, right? X is some fixed value. So we can take this x squared and just bring it out in front, right? That doesn't have to stay in the limit because there's no n's in there. This time I don't need to put it in absolute values because it's x squared, so it's going to be positive anyway. And then, so up top we've got 1 over 2n plus 3, 2n plus 2. I don't need absolute values in the limit either because we're letting n get huge and this whole thing is positive. You know, every term is positive. So let's see what's going on. So x is some fixed value. X squared is just some fixed value. So what we want to do is focus on this here. And this limit, as n gets huge, this goes to 0. And then I take that 0 and I multiply it by whatever x squared is. It's still going to be 0, though, in the end. So this limit is 0, which is less than 1. The limit is always less than 1 for any fixed value of x. That means that we always get convergence. Like no matter what value of x we plug in, we perform the ratio test, oh, it's going to converge. That means I can stray as far from the center as I want and still get convergence. The radius of convergence is infinity. So now we're going to just talk about what happens at the endpoints a little bit. So remember that with the ratio test, you get convergence when that ratio or when that limit is strictly less than 1. You always get divergence if it's greater than 1. But with the ratio test, if it was equal to 1, we weren't sure what happened, right? It was inconclusive. So that means that after we're done performing the ratio test for these power series, we're not entirely sure what happens at the endpoints, right? If we have a finite radius, we're not entirely sure what happens with these endpoints. So when we're in that situation, we just put in each endpoint. We test each endpoint individually and say, okay, well, what series does this give me if x takes on this value or that value, and then perform whatever convergence tests we're able to perform on that. So we're going to find the interval of convergence. So note the difference here in what they're asking us for. We're going to find the interval of convergence. That means we need to address what's going on at the endpoints. So here's this series, x to the n over n. We'll just note that the center is 0 there. And so now we're going to consider non-zero values of x. Our nth term is x to the n over n. Our n plus first term is x to the n plus 1 over n plus 1. So the limit, as n approaches infinity, of u sub n plus 1 over u sub n So u sub n plus 1 is x to the n plus 1 over n plus 1. I'm going to multiply it by the reciprocal of u sub n. So that's n over x to the n. Do some canceling on those powers of x. So we just have a single factor of x up top. X times n over n plus 1. I'm going to grab that factor of x, yank it outside, out of the limit. When we do that, we have to keep it inside absolute values. And now we just want to evaluate this limit. So x is some fixed value. Absolute value of x will be some fixed value. Let's see what's going on with this limit right here. The fraction n over n plus 1, as n gets huge, that gets closer and closer to 1. You could see that in a couple of ways. You could multiply the top and bottom by 1 over n. You could apply L'Hopital if you want. You could also just sort of conceptually see that these are fractions where the top and the bottom are both getting huge, but the bottom is only just 1 more than the top. So that overall, that difference shrinks, right? The overall difference that it makes in relative to the size of n is shrinking. So think about like 100 over 101, 1,000 over 1,001, 1,000,000 over 1,000,001. Those ratios get closer and closer to 1. And that means overall, now if I take that limit of 1, I got to multiply that by the square root of x, or not the square root, the absolute value of x. So the result is absolute value of x, which we know that we will get convergence when that is less than 1. It's centered at 0. So absolute value of x less than 1 gives us a radius equal to 1. So far, we know that it converges on the open interval from -1 to 1. We need to test the endpoints. So when x is equal to 1, the series that we get is 1 to the n over n, so that's just 1 over n. And this series diverges. It's the harmonic series, or a p series, where p is equal to 1. So we don't get convergence at 1. Let's see what's going on when x is -1. When x is -1, I have -1 to the n over n. Now, this series converges. This is an alternating series. If you use the alternating series test, the terms are, or the absolute value of the terms are monotonic decreasing. And the terms approach 0. So as using the alternating series test, this converges. And that means that the interval of convergence is, let's see, now we can include -1. We get convergence at -1, so that's closed on that side. We don't get to include +1, so it's open on that end. So there's our interval of convergence. And just as a quick heads up, generally you'll probably see me abbreviate interval of convergence as IOC in going forward. So when we're asked to find the interval of convergence, we're going to start out, it's just like these problems where we are finding the radius of convergence. We just have to do the extra steps to see what's going on at the endpoints, and that means we're going to test each endpoint and see if the resulting series converges or not. All right, so now let's find the interval of convergence for this series. It's alternating, looks like. Oh, and the first thing we want to observe is where is it centered. So this is centered at -1. And now we're going to consider some fixed value of x that's not the center. So for x not equal to -1, let's see, our nth term, our n plus first term, and we're going to set up our limit. So there's the n plus 1 term. I'm going to multiply by the reciprocal of the nth term. And we'll do some canceling. So the 2 to the n up here cancels. We're left with just 2 to the first. The x plus 1 to the n on the bottom, that all cancels, and we're just left with x plus 1 to the first right there. And we can ignore the those powers of -1. Those just affect the sign, and they're sitting inside absolute values anyway, so we'll ignore that. So what we're left with is x plus 1 over 2. So now we're taking the limit as n approaches infinity. There's no n's left, right? There's nothing for n to do. This thing is fixed. Whatever value of x we're looking at, this whole limit, it's just absolute value of x plus 1 over 2. And to get convergence, what we need out of this is for this to be less than 1. So if the absolute value of x plus 1 over 2 is less than 1, the only way that happens, I'm going to come over here on the left, the only way that happens is if the absolute value of x plus 1 is less than 2, and that means that x plus 1 without absolute values has to be between -2 and 2. So this gets us part of the way to the interval of convergence, right? Just we can subtract 1 from all three sides, and we get -3 less than x less than 1. So far we know that it converges on the open interval from -3 to 1. But we need to figure out what's going on at the endpoints. So let's test the endpoints. So if x is equal to -3, we get the series, let's see, -3 plus 1 is -2. So we have negative 1 to the n, negative 2 to the n over 2 to the n. Doing a little algebra here on what's going on up top. Negative 1 to the n times negative 2 to the n. Well, that's negative 1 times negative 2 to the n, or 2 to the n. So this series is really just the series where every term is 1. That diverges. We could see that pretty immediately. It fails the nth term test, right? Those terms do not approach 0. If x is equal to 1, then we have negative 1 to the n times 2 to the n over 2 to the n. Doing a little algebra here, right? The 2 to the n's cancel, and we just have negative 1 to the n. That's this series. What do you think that series does? And why? This series diverges for the same reason that the last one does. The terms do not approach 0. So we don't get convergence at either endpoint, and that means that the interval of convergence is negative 3 to 1, the open interval only. Okay. So we're going to finish up this section talking a little bit about differentiation and integration. So let's say we have a power series and we have some radius of convergence that's bigger than 0. So then if that radius of convergence is r, then we get convergence for sure on the open interval c minus r to c plus r, right? So you take your center plus or minus your radius of convergence. So on that open interval, your function defined by the power series is continuous, it is differentiable and integrable. And we can use the usual methods, which for us is going to be just the power rule, right? These power series are like infinite degree polynomials. So using the power rule, we can find a power series for f prime. Here's a typo here. That should be f prime of x and the integral of f. Both the derivative and integral have the same radius of convergence. So if you know the radius of convergence for a series and you get a new series by taking the derivative, you don't have to do the ratio test again. It's going to inherit the same radius of convergence. It is important to note that behavior at the endpoints may vary, so you have to retest the endpoints. So let's take a look at this power series. So here we're defining the function by the power series of n equals 1 to infinity, the nth term being x to the n over n. We actually worked on this series. This was an example if I can find it, 46. Okay. So we worked on this in example 546. And we found that the radius was 1. And the interval of convergence for f of x is the half open interval, closed at -1, open at 1. We know from theorem 29 up here that f prime and the integral of f will have the same radius. So now what we want to do is just find the series, the actual series for f prime and for the integral of f, and then test the endpoints to see if the interval of convergence changes at all. So let's find f prime. So f of x, as given, is this series here. And so that means f prime let's see, I'm just going to use the power rule on this. So for each term, for the nth term, if I take that derivative, I'm going to get n times x to the n minus 1. And then this is over n because I'm bringing over that denominator term here, or that term in the denominator. And we can do some simplifying. All right, so this is the series whose terms are x to the n minus 1, where n starts at 1 and goes to infinity. You could, if you want, rewrite this, sort of shift the value of n. This is the same. You know, notice that if n is 1, then you get x to the 0. If n is 2, you get x to the first. So you could rewrite this as the series where n starts at 0 and goes to infinity of x to the n. Their equivalent series. Either way you look at it, let's say I take this form of the series there. We're going to just find the endpoints. I know the radius is 1. So endpoints. So if I put in -1, that gives me the series -1 to the n minus 1. That diverges by the nth term test. And if we put in x equals 1, we get the series where every term is 1. Again, that diverges by the nth term test. And so that means in the series for f prime, we don't get convergence on either endpoint. So the interval of convergence for f prime of x is the open interval from -1 to 1. Let's try the integral. So let's find the series for the integral of f dx. Our series for f of x is x to the n over n. So the integral of f is going to be this series. So if I integrate each term, then we have x to the n plus 1 over n plus 1. Notice I still have this factor of n down there, so I got to bring that with us. It's this, and then of course plus a constant, whatever that series is, and then plus some constant. So let's see what this series does at the endpoints. When x is -1, we get the series -1 to the n plus 1 over n times n plus 1. And this series converges by the alternating series test. And when x is equal to positive 1, that gives us the series 1 over n times n plus 1. I'm going to go ahead and just write that as n squared plus n this time. This series maybe takes a little bit more thinking to kind of see what it does, but you can use the limit comparison test or the direct comparison test, and you'll see that it converges if you compare it to 1 over n squared. Right, so we know that 1 over n squared, that's a convergent p-series because p is equal to 2, which is bigger than 1. So now, since we get convergence at both endpoints, the interval of convergence for the integral of f is the closed interval from -1 to 1, closed on both ends.